call that a day.
Well, it's a good thing we didn't have more tests this semester. I didn't think I could grade 3 of them and get them done. I don't have your tests graded yet. And also, we're just barely gonna finish, I think. If I would have had one more test between the lecture or the review day and the test, I think we would have been a week short. So hopefully everything will work out. You guys are the last test to be graded. Unfortunately, I'm sorry I don't have them back yet, but they'll be back shortly, probably next time. So today we want to continue what we're doing on line integrals. And
Can you move the camera to the right?
yeah, that would help. I forgot to do that, didn't I? Where's that thing? There it is. Yeesh. Gremlins. All right. I can hardly see that. I think that's readable. All right. So line integrals continued. Okay, there were 2 line integrals. The scalar line integral, meaning the output is a scalar or a number. Was given this notation, the integral along C, a parametric curve of a function. You can do it in any number of dimensions. Let's do it in 2 dimensions, just in the plane. F of x, y, ds means the limit as the number of increments goes to infinity of the sum k equals 1 to n, f of xk star, yk star, any point along the kth segment, which we can also write as write it this way just to be more explicit, f of tk star, y of tk star is xk star, yk star. Delta sk was given. See, can you see all of that online? Did I go too far? I think we need to stop just in
Yeah,
time.
we can see.
Yeah, just got it. Thank you. Scalar line integral for a curve C, smooth, meaning it has a continuous derivative, given by the vector valued function r of t, with t running from A to B. And what is delta sk? It's the length of the kth line segment. The idea is you have a curve in the xy plane, and over at some surface z equals f of xy. So you're taking the height of the surface above this curve, integrating along between these points x of t0, y of t0, which is also x of a, y of a. The endpoint, x of tn, y of tn, in increments, which is also x of b, y of b. And sk at the kth increment, delta sk, is the arc length of the kth piece, which we recall is the integral from tk minus 1 to tk, where you partition interval A to B. With t going from t0 to t1, t1 to t2, all the way down to tn minus 1, tn, n increments, parameter t. of square root of the x dt squared plus dy dt squared dt. That is the definition of arc length. Since this is a smooth curve, this is well defined. We say that's the case arc length. Right? That was the scalar line integral definition. And we said that could be evaluated as a line integral along C f of xy ds, the notation, is equal to the line integral from A to B f of x of t, y of t, square root of the x dt squared. Sometimes they put x dot squared, it's a lot less notation. Plus dy dt was how you could evaluate it. What it means geometrically, one interpretation is that you're just taking the basic line integral along the x-axis in calculus 1, but now you're curving the rectangle so they go up to the surface, and you've got kind of a curled, set of curled rectangles sitting over the surface. Sitting over each interval instead of rectangles sitting along the x-axis, and that's the only difference. That's what you're computing. Some of those rectangle areas like that, and you can compute it this way. All right. And so they like to think of the infinitesimal arc length ds as being square root of dx dt squared plus dy dt squared dt. For all this is, in fact, ds dt, right? Because you take the derivative of this integral from this to t, it's the integral. Derivative times dt is that, so that's ds. So that was the scalar line integral. I'm just going to set this up. And there were some problems we could do with that. So, for example, evaluate line integral along C of x, y, ds with C given parametrically by x equal t, y equal t squared, the parabola. Well, actually, here. Line 2t plus 4 y equals 3t plus 1. All right, so I'm going along this line, t running from 0 to 1. What's that line integral? What we do is we say that this line integral is evaluated if we call that equation 1. Is the integral t going between its two endpoints, 0 to 1. X written as a function of t is 2t plus 4. Y written as a function of t is 3t plus 1. And then what is ds? Well, it's the square root of dx dt is 2 plus dy dt is 3 dt. So it's just that integral. Well, let's see, this is square root of 13. Integral from 0 to 1, and then this gives me 6t squared plus 2t, and 12t is 14t. 4t, and I can do all this, right? Square root 13 times 2t cubed plus 7t squared plus 4t, 1, 2 plus 7 plus 4 is 13 square root 13. So there's the value of that line integral. What does it represent geometrically? Gather from what I wrote down there, what it represents geometrically? What you can think of this as if you want, is the surface z equals xy, which isn't real easy to draw. Right along the x-axis and y-axis, it's 0, and then it gets higher in the middle, so it's kind of like that. As t goes from 0 to 1, this is a line, right? If x equals a linear function, at plus b, and y is a linear function, ct plus d, then this is sweeping out a line, remember? And by plugging in t equals 0, you get x equals 0 plus 4 is 4, 0 plus 1 is 1. So it starts at 0.41, 1, 2, 3, 4, in the xy plane. And it ends when t equals 1, 6 plus 4, so it's 6, 4. So the curve is actually this straight line segment from 4, 1 to 6, 4, going, I'll put a direction on it. Since it goes from here to here, we'll put an arrow showing the way it moves. But we're finding the area of the curtain, if you like, hanging down from the surface z equals xy to this line segment. That is the integral of xy dx. See. But I mean, this is just a nice picture. You can just evaluate it without.
The 2t plus 4 and the 3t plus 1, that was given at the top, right? You didn't have
Yeah.
to find that.
Yeah, you have to give me what curve you're integrating along and what's the integrand, and then I can write down the line integral. Yeah.
Where'd you get the 0.64 from?
6, 4.
On the graph.
Oh, I put in t equals 0 and got. I put in t equals 1 and got 2 plus 4 is 6. 3 plus 1 is 4. So when I plugged in t equals 1, that's the other endpoint. So I know it's a line because x is a linear function, y is a linear function, at plus b, ct plus d. So I know it's a line segment, and I just find the endpoints by plugging in t equals 0 to get the first point, t equals 1 to get the second endpoint. That's how I found it.
Thank you.
Yeah. What is another application of this vector line integral besides finding surface area? We said last time in passing that you can use it to find the mass of a wire. If you think of this instead as being a wire of variable mass, and the mass and the density function is xy at each point along this curve, then this is actually the mass. Let's take that note then. That's what we wrote last time, but mass is the integral along C of f of x y ds with mass of a wire along C of mass density f of x y is the second interpretation. We have a circular arc. Is number 37. Y equals square root 9 minus x squared. Is a curve. X going from 0 to 3. And suppose its density function is x squared root y. What uses delta instead of f? Find the mass of the wire. Right? All you have to do is compute the scalar line angle. So you say the mass is the line angle along this curve C of the density function x squared root y. Yes. But wait a minute. How do I apply the formula? I first have to write this parametrically. So what's the easiest way if you have y already written as a function of x? It's usually easiest just to let x equal t. You try that first. If sometimes you have to go something more exotic. If it's a circle, then maybe use cosine and sine. Let x equal t, and then y will be the square root of 9 minus t squared. Let me try that first. And t will go from 0 to 3 then. I guess it's on. All right. So now you just have to replace x and y with the functions of t that they are, and let t go from 0 to 3. And let's see, x is t, and y is right. So square root of y is square root of the square root of 9 minus t squared. dt square root y. Now I make a substitution. This is the integral from 0 to 3 of t times the fourth root 9 minus t squared. And you can see how to make a substitution in there, right? Let u equal 9 minus t squared be the inside function. When you have a function of a function, you try that. In that case, du is the derivative dt is minus 2t dt. Oh, I almost have that within a constant, right? So if I multiply that by minus a half, I then get minus a half du to replace t dt that I do have there. Then I'm left with a t cubed still. Not with a t cubed, this fourth root t. There we go. So if I replace my t dt with that, I'll get the integral. Let's see, when t equals 0, u is 9 minus 0 squared is 9. When t is 3, u is 9 minus 3 squared is 0. So this integral goes from 9 to 0 over u. T dt gets replaced by minus a half du. And then this is fourth root of u. So it becomes that. So now this is u to the 1/4. It's easier way to write it, right? So I have minus 1/2 u to the 5/4 over 5/4. Evaluate at 0 and 9 and take the base. Well, let's see. This is 4/5 times minus a half is minus 10. Minus 2/5. 9 to the 5/4. 0 to the 5/4. Well, square root of 9 is 3, so it's the square root, fourth root of square root 3. Let's say I got 9 square root 3, I guess. So minus 2/5 square root 3 minus 18 square root 3.
Shouldn't the 9 and 0 be the other way around? Like two things up?
Oh, yeah, it should be 0 minus 9, shouldn't it? Let's see, what have I got wrong here? Yeah, good, yeah, you're right, thank you. 0 minus 9 to the 5/4. Now this is plus, which is what it's supposed to be. Thank you. Those are applications of the scalar line integral. Now we can do what's called the vector line integral. And boy, there's all sorts of new notations thrown in here. It's my head's been looking at it. I like to just boil it down to these two and think of the others in terms of these two. The vector line integral you have line integral of a vector. Of a vector field f of x, y in the plane along a curve C given parametrically by a vector value function r of t, t going from A to B, just for simplicity. Is this. We give it this notation, f dot dr is just notation along C, and it means the line integral, the scalar line integral, f dot t ds. That'll be the definition. Where, what's t? Not before. This goes a ways back, calculus 3. We're saying t last semester, everybody? Unit tangent vector. Oh. How can you compute the unit tangent vector? You compute the tangent vector, r prime. That's the tangent vector, and then divided by its length to get a unit tangent vector. R prime divided by its length is the easiest calculation formula. This is not the way it's always defined, but it's the easiest way to compute it. Where r prime isn't 0, you can compute it that way. All right, so that'll be the vector line integral. You can evaluate it as a scalar line integral. This is one of the first things that comes up. Sometimes they'll say evaluate f dot dr, and sometimes they'll say evaluate f dot tds. It's the same thing. This one is defined as this one, right? And so we already know what the scalar line integral is. We just take the scalar line integral of this dot product, right? This is now a function of x and y that you integrate by scalar line integral. Now there's a nice theorem. How are we going to evaluate that thing easily? Maybe it's a mess. Remember, the scalar line integral is always nasty because we had that square root in it, right? It's square root of dx dt squared plus dy dt squared. Usually you couldn't integrate that. I picked a couple of cooked examples we could do, right? But generally that square root in there makes this intractable for actually computing anhydride. It's just estimated as accurately as you want on the computer or something. But it has this nice result. I want you to see this derivation. If you take f dot dr, that means integral f dot t ds by definition. But t is r prime divided by its length, right? The unit tangent vector. And what's ds? ds, we said, could be written as square root of x prime squared plus y prime squared, right, dx dt squared plus dy dt squared dt. So, but what is this? This is actually the length of r prime. It's the x component squared plus the y component squared of r prime. So we can replace t with this, replace ds with length of r prime dt. Marvelously, these two cancel. This goes from a to b since we're now integrating over t instead of taking the line intervals. So by our evaluation formula for scalar line integrals, this was, what do we call it, 1? Give that a number? Evaluation formula for scalar line integrals, was that 1 or not? Nobody is awake. Okay. All right, so maybe by 1. By our first boxed equation anyway. Yeah, the first formula I wrote up for evaluating the scalar line integral, I said it was equal to the integral from a to b of f of x of t, y of t, square root of dx dt squared plus dy dt squared dt. This formula for the scalar line. So we can evaluate this by doing this. What was that? Did I give that a number? It was right at the beginning.
It's from 0 to 1.
The example went from
Oh,
0 to 1. This is for general, it goes from A to B, whatever the curve is. Yeah, so anyway, it was right in the beginning. By this equation, you can replace ds with, this is length of r prime. So you can apply that formula, this formula right here. I erase this. Circle 1 on your paper next to this one and then say by 1.
So I guess the answer to the question is yes.
All right. What you get then is integral from a to b of f dot r prime b. That's the formula. For computations, you can evaluate f dot dr, which means the scalar line integral, by simply computing the integral from a to b f of x of t, y of t, this is formally when I write in all the details, dot r prime of t. So define a vector line integral this way, evaluate it this way. Right? Look, that nasty square root is gone. It's not so bad. Furthermore, this vector line integral is very important. It's the way we define work in physics. So it's used to calculate potential energy, for instance. Oh, we should give that a number. You're right. This will be number 2 then. So number 1 evaluates the scalar line integral. Number 2 evaluates the vector line integral. Thank you. There we go. Suppose f of x, y is x squared plus y squared. X and b and x and y. F of x, y, a vector field, is x squared yi plus 4j. Well, that's your vector field. Remember, vector field associates with each point in the plane a vector. So at each xy This is the vector you compute. And suppose you're moving along the curve R of t which is e to the ti plus e to the minus tj. And c going from 0 to 1. And I'll say evaluate the vector line integral. F dot dr. This is what's beautiful about this notation. What does this really say? This says integral f dot dr along C is the integral from A to B, the parameter values, f dot dr dt dt. That's the easy way to remember it, right? F dot dr dt dt. So dr, just think of it as dr dt dt, and it all. So let's do that here. This is f. We'll integrate along the parameter values from 0 to 1. And then f is this x squared yi evaluated. Here's the formal notation, or the written out notation. You have to write x as a function of t and y as a function of t. It's f along the curve. So f gets replaced instead of by x squared yi plus 4j, you write it as e to the t squared e to the minus t I plus 4j. That's f as a function of t, right? X squared y I plus 4j. Dot product that with r prime. Well, what's r prime? Derivative e to the t is e to the t. And the derivative of e to the minus t is minus e to the minus t. So that's r prime. Just change the plus to a minus. Dt. The formula 2 says there's nothing more to it than computing that dot product and taking line integral. There's no nasty square root in there. So let's see. This is all e to the t. First component times first is e to the t times e to the t is e to the 2t. Plus second times second minus 4e to the minus t. So first times first gives this, second times second gives that. T. That's not so bad, right? Integral of e to the 2t is 1/2. Integral of e to the minus t is minus e to the t, so plus 4e to the minus that. Plug in 0 and 1 and take the difference, right? So I get 1/2 e to the squared plus 4 over e minus 1. Plugging in the top is 1, and then plugging in 0, I get 1/2 plus 4 is 9/2. There's the value of that vector line. All you got to do is take f dot dr dt dt, and so it's actually not so bad to evaluate it. Now, finally, one thing that's frustrating in this book is they develop work gradually. And it just never get a grasp on it till now. So I hope we'll get a grasp on it finally. What is work? It's different than the lay definition of this, right? If I take a 100-pound barbell and hold it over my head all day, how much work have I done? 0. Work is 4 times distance. I haven't 4 times displacement. I haven't displaced it at all. What's more, if I'm pushing up and it gradually presses down a little, I've actually done negative work for all my effort, right? What is work? For along a line, this is first definition, along a constant force, F, displacing an object an amount D, which could be negative, has done work force times distance, or force times displacement, really could be. All right. So I'll do that in the first part of the book. Then they'll say work along a line. What about work along a line? Along a straight line, where the force is directed along a line. Suppose a force pushes something from displacement D. Now what's the word if it's a variable force instead of a constant force? Yeah, right. Because what happens is you want to increment this into little pieces and say, along each little piece, the force is approximately constant. So the work ought to be the limit as the number of pieces goes to infinity of this constant approach, sum k equals 1 to n of f of x k star, the approximate constant work on the kth interval, times delta xk, the displacement along the kth interval. And so it's constant force times distance from this one, but broken up into a lot of pieces. In the limit, this gives the same value regardless of how you partition it and so forth. And by definition of definite integral, this is just a direct definition with a capital F instead of a little f. This is exactly right. The integral from a to b f of x dx is the work done along a line by a force placed along. Now, really work is more complicated than that. Pushing along a line so these are built up in different pieces all through the book. A variable force f of x, y in the plane. So it could point any direction. What's the work? Well, actually, let's just go straight to the thing. Pushing along a curve. What we're going to do now is say pushing along, pushing an angle. Let's do that. Pushing at angle. The work is now equal to the integral of f dot t ds along C, along a general curve. And the idea is this. The work is actually the force along the direction you're moving, and you don't count the force that's perpendicular. If you have a curve like this on the plane, here's C, this point to this point, and there's some force field in here, right? And it's pushing like this here, and pushing like this here, and pushing like this here, like this. And so you're moving through some sort of a force field, gravity or whatever kind of force it is. Along this line, what's the work done by the force? What you do is you take the component of the force along the tangent of the path. So you break the force into a component along the path and a perpendicular component, right? And what is this one? This is the projection of the force onto this unit tangent t. Right? If you have a little unit tangent vector here to the curve, r prime over its length, it's projecting the force onto the tangent vector. And what you want to do is integrate that. You don't count the perpendicular component. Sometimes I call this F parallel and F perp for the two components, vector components. So this is like F component force perpendicular, and this one is the component of F parallel to that. What you want to do is say the work is the integral along the curve of F parallel. Yes, the component of force that's pushing you along the path. Don't ignore the part that's perpendicular to the path. I mean, ignore the part that's perpendicular to the path. only count the force that's pushing you along the path. That'll be the work. But F parallel, what is F parallel? Flip on one of these we're gonna show here. Well, if you think about it, what is this? What is this component of the projection when you're projecting it onto a unit vector t? Right? The projection of F onto a vector t is F dot t over length of t squared t, right? That's the projection of F onto t. But what's the length of t? 1, yeah, it's a unit vector, right? So this is 1. And so it's just F dot t in the direction t. So what you have here when you integrate this is just the integral from a to b of F dot t ds. Work is just the vector line integral. What's also known as integral F dot dr. In other words, work is the vector line integral. What it is it's integrating the vector component of force along the path. That's the most general definition. Now you see all these other ones you did earlier, but are all special cases. They break it up into actually one more piece than this kind of half in the last 2 cases. So now you can ask interesting questions like this. What's going on? Suppose the force is 1 over x squared plus y squared I plus 4 over x squared plus y squared j. You're acting, a force like this is moving, acting on a particle that moves along a path. How much work does it do? We call that the work done by F, and then if you do your work to push it back, it's the work against F. Anyway, how much work is done by F? And RFC is this path semicircle or quarter circle of radius 4. Wonder how much time is there? How much work is done there? How could I do that one? Well, the work is the vector line integral, right? I say work equals integral along C F dot dr. The way you evaluate these things is to integrate from A to B F dot dr dt dt. Here and there. And F, well, let me rewrite the R of t here, if I'm using a quarter circle, what should I use for a circle of radius 4? Could use 4 cosine t I and 4 sine t j, right? That's how we make parametric circles. X equals cosine, y equals sine, give you the unit circle from trigonometry. 4 times that gives you the circle of radius 4 at the origin. So there's my parametric curve, and now 1 over x squared plus y squared. First component of f, well, that's 1 over x is 4 cosine t. Plus y squared is 4 sine t. So there's the first component of f. 4 over the same. X squared plus y squared. There's f, I suppose. See if I can make this work. And then it's got a dot dr dt. What's dr dt? Well, r is this vector here, so its derivative is minus 4 sine plus 4 cosine. That's all integrated with respect to t. Yes, fair enough. So there's what I need to evaluate, and I go from the beginning to the end. To do a quarter circle, I'll use 0 less than or equal to t less than or equal to pi over 2, because we recall t is the polar angle for the unit circle cosine t sine t, and so it's also the polar angle for a circle of 4 times that radius. So this will go from 0 to pi over 2. There it is. Well, this is easier. We hope for probably, right? What's 4 cosine squared plus 4 sine squared? 16 cosine squared, 16 sine squared is 16, right? Cosine squared plus sine squared is 1. So this is 1/16. This is 4/16 or 1/4. Just by trigonometry, right? Sine squared plus cosine squared equals 1. And then dot 4 sine t, 4 cosine t, dt. We just have to evaluate that. This is integral from 0 to pi over 2. 1/4 sine t. This times this plus this times this. 1/4 sine t plus cosine t dt gives us, let's see, 1/4 of sine t integrated gives us minus 1/4 cosine t. Integrate sine t and we get cosine t and we get sine t. Need to plug in 0 and pi over 2 and take the difference. Well, cosine pi over 2 is 0 and sine pi over 2 is 1, so the top endpoint gives us 1. The bottom endpoint, cosine is 1, I get minus 1/4, and sine is 0. So this all adds up to 5/4. And then you ask yourself, well, what if R of t is in feet and F of t is in pounds, right? Pounds is the force. And what's the units of work?
Foot pounds?
Yeah, in the English units it's foot pounds, right? It's force times distance, right? So it's units force times distance, just like the constant case, it's foot pounds. And you're right, in the international system, it's newtons, yeah.
I was like, wait.
You're American, you can go foot pounds still, right? Follow the Brits.
I don't like foot pounds.
Yeah, I
I
don't,
don't like
I
the
don't,
US
yeah,
system.
a lot of people don't. All right. All right, so let's play about this then. For the people who like the metric units, we can make this meters. And this could be newtons, and if it's meters and newtons, then the answer is in Newton meters, force times distance. People get tired of writing that, so they call them joules. Newtons times meters. So that's work. Moreover, I'm going to introduce this one as notation. The book introduces this a little differently. I think I got that back into the board here. Don't I? The book further can, I think they confuse this. I don't want to pick on the book. It's a classic book. It's been in major circulation for, geez, I don't know, since at least the early 80s. So it's about 4 years older. I don't know when the first edition. But I wish they would do this differently. Suppose I have an integral that looks like this, f of x, y. So I'll call this notation, even though the book will introduce a little different. Dx plus g of x, y. What does that mean if I write that notation along a curve? We can let this denote integral f dot dr, the vector line integral, with f of x, y, denoting the vector with components f of x, y, g of x, y. And this comes out to be the same thing. Then by our theorem, but we'll call this a definition for us. We'll let this just be another notation for that. Then our theorem is 2, says that you take this dot dr dt, is this dot dr dt, so it's integral from a to b of f of x, y dot dr dt is f times dx dt plus g times dy dt, all integrated with respect to t. This is what equation 2 says if you interpret this line integral like this. Oh, that's easy. You're just thinking of dx is dx dt dt and dy is dy dt dt. You just have this one evaluated this way. Just replace dx by dx dt dt and dy by dy dt dt. It's just interpreted as a vector line. So they ask you to do a few of those problems in this section. Half the trouble is just getting used to all these different notations. Hence, integral f of x, y ds is the scalar line integral of a scalar function. But if I write integral f dot dr, or if I write integral f dot t s, or if I write integral f of x, y dx plus g of x, y dy, sometimes you'll leave one of these out. You're just thinking like g is 0 along c. These are all mean the vector line integral. And also, if you write this one, f dot dr dt, dt is the evaluation formula for it. These are all notation for the same vector line integral. This gets confusing. And this one evaluates as integral from a to b, f of, this is formula 1, of 1 these all evaluate by 2 this way, where f has components little f and little g. Last case. So these all mean the vector line integral, and this will be the scalar line integral. So now we can try and do one of these in the other notation. And you replace the x with the x dt dt, dy with dy dt dt according to this. Oh, I know what I did. I didn't plug this in. That's why it keeps going.
Throw the camera back for just a moment.
Yeah. Okay. I think I can start on this next one without, let's see. Here's another example. Suppose I want to integrate y dx minus x dy. How about that one along the curve C? Evaluate this. Well, I need to say what the curve C is. For the curve C, that is this triangle. 1, 0, 0, 1, 0, 0, traverse counterclockwise like this. So we go once around the block, here, triangular block. That'll be C. How can we evaluate that one? Well, we just rewrite this as integral t going from a to b, following we should call that equation 3. Tell you what, let's do that. Call this one equation 3, that the integral f dx plus g dy, just replace dx with dx dt dt and dy with dy dt dt, go from a to b instead of writing along c. That'll be 3. Now we can say by 3, this is equal to y dx dt dt plus x dy dt dt. T going along this curve here. Well, we have to break it up into 3 pieces. What I'm going to do is I'm going to let C be the union of C1, C2, and C3. And I'm going to call this one C1, this one C2, and this one C3. And I'll go around like that. So I'm going to take this as the integral along C1 plus the integral along C2. This is minus, I'm sorry, plus, it's minus. Plus the integral along C3. The same. And so the integral along C is the sum of these 3 line integrals, right? This is going from point A to point B, point B to point C, and point C to point T, just like you did. Calculus 1 on the line. And along each of these curves, I just have to write the different parametric form. C1, when I'm moving along here, I can let x equal t, and y equals 0, and let t go from 0 to 1, and that'll sweep out that one. Along C2, if I want to go up this one, now this is the line, what is it? My intercept 1 and slope minus 1. So it's y equals minus 1x plus 1, right? Mx plus b with slope m minus 1 and y intercept 1. That's that one. So I can make this one parametrically by letting x equal minus t, let's say. And x and t can go from 0 to, let's see, from minus 1 to 0. It's too hard. And that way x goes from 1 down to 0, right? If it's minus t. And y is equal to t. T plus 1, I guess. So it starts at 0 and goes up to 1. There we go. So x is minus t and y is t plus 1 along this path. And then along this path, I could let x equals 0 and y equal minus t, t going from -1 to 0. There's lots of other ways to write this too. I would do it. So y starts at 1 and goes down to 0 according to this prescription. Just keep your direction correct. It turns out, I haven't written it yet, but the line integral, if you do a scalar line integral, it doesn't matter which direction you go. The scalar line integral is the same. What it's doing is finding the area of that curtain. It's adding, if you go one direction, it increments in that direction. You go the other, it increments in that direction, positive arc length. But the vector line integral in the opposite direction is minus the vector integral in the other direction. And so we have to be careful about which direction we move along each of these. We'll get minus the result. All right, so now the line integral is the sum of these three things. The integral on the first curve, t goes from 0 to 1. Y is 0, so there's nothing. Minus x is t, and dy dt is 0. dt, it adds up to nothing, right? Along the first part, y is 0, and the second part, dy dt is 0, so it's 0 minus 0. Right? Now along the second curve, C2, t goes from -1 to 0. And now y is t plus 1. The x dt is -1. Here's x is minus t, so the x dt is -1. Minus x would be minus a minus t. dy dt is 1. Y dt is t. All integrated with respect to t. This is the integral along C1. This is the integral along C2. And the integral along C3, t goes from -1 to 0. Y is minus t dx dt is 0, so this one's 0. Minus x dy dt is 0 times something. So these two integrals just vanish, right? All you have, line integral becomes down to this integral along C2, which evaluates this way, is the integral from -1 to 0. Let's see, minus t plus t, these cancel, right? Here's a minus t, and here's a plus t. This is integral of -1. T is minus t, plug in -1 of 1. So I get -1 minus, there's too many minuses here. This is very bad. So I'm subtracting, I'm putting in 1 at the top and getting -1. At the bottom, I get minus t, but t is -1, and then I subtract the bottom. So it's minus, minus, minus. All right. So -1 minus a 1 is -2 then.
Why did the bounds change?
Oh, when you change it to evaluate by this formula 3 or 2, whichever one you're using for the problem, you can slide the thing back over. It's obviously when I went from here to here, when I rewrite it, oh, you know what? I should have done it here, shouldn't I? Maybe that's what you're pointing out. This should be from the A to B along C1. I guess what I should do is up here, say this is line integral x dy, y dx minus x dy along C1 plus the integral along C2 are the same, y dx minus x dy. Oops. Plus the integral along C3, y dx minus x dy. So I'll write this one as the sum of these three integrals. And then I should call these A to B. Once I put dt, I should go to A to B. So A to B along curve 1, A to B along curve 2, and A to B along curve 3. I should have changed them here, shouldn't I? It's easy to get sloppy. All right. So once you change the dt, then you go from A to B, the values of the parameter. And before that, you always put C.
I meant you go from 0 to -1, and then the next line you do 1 to -1 on the left
Oh,
side of the board.
Yeah, well, that's my other mistake. I'm doing this too much at night. Yeah, it should have been 0 to 1, shouldn't it? -1 to 0.
Talking about the,
Yeah, yeah, this was -1 to 0, and then I wrote -1 to 1 down here. Yeah, there should have been -1 to 0. So there's a book. This is actually a book problem. -1 to 0 of -1. So it's minus t evaluated at 0, 1, and take the difference. So the top one is 0, and the bottom one is subtracted, and its value is minus a -1. So that line there actually adds up to -1, not minus. All right, now let's make the comment about the direction. So the note is, it does not matter in the scalar line integral which way you traverse the curve. If you call minus c traversing the curve in the opposite direction, you get the same value. What happens is you just let t run from the one endpoint to the other, and this ds is always the positive square root. It gives you the same value. It's just, the arc lengths are positive whether you're moving from one end of the curve to the other or from the other back. Arc lengths of ds, delta sk are always positive. But if you do the vector line integral, it's f dot dr is defined to be integral f dot t s. And what happens is integrand changes direction depending on which direction you're moving, right? So this is actually minus the integral f dot t ds along the curve minus c, which is minus integral f dot dr. So the integral along minus c is minus the integral along c. Simply written this other way. I mean, that's correct, but the other way of writing is the integral along minus c f dot dr, taking minus each of these sides, is minus the integral along plus c. It's because this changes sign depending on which direction you're moving. If you're moving this way, t is a unit tangent vector in this direction, from this point to this point, and so f dot t, if your force field is like this, will have the projection on here in this direction. But if you're moving, so it's along c. But if you're moving in the opposite direction along the curve the other way, you call that curve minus c. Then t goes this way. It's always tangent in the direction you're moving, right? Here's t. And so f dot t at the same point. Oops. Same point. So now t is pointing this way, and the force field is this way. And so f dot t is actually negative now. Here's f. Here's t pointing backwards, opposite direction. So f dot t is minus what you get moving this direction. Oh, if you just let, you just write it parametrically, so the parametric curve moves from here to here. Like you get it right from 1 to 0 instead of 0 to 1 in the formula. Right? You had integral from 0 to 1, f of x to t. The easiest way to do it is that. Let's see. If that's the motion along C, then it'll take you from point A to point B. If you go along minus C, you just go from 1 to 0 with the same integrand. And that would take you from point B to point A. To reverse the order here, to change direction, that makes minus this integral. That goes 1, this integral, this integral. So the evaluation formula shows it also. All right, so that's the line integral then. I think that's most of the examples we need. Maybe I can put up a fun theorem in the next section to whet your appetite then. Theorem that goes with these. Now, why are these conservative forces so important, right? It makes a generalization of the fundamental theorem of calculus. How about that? What could be more important than the fundamental theorem of calculus? Maybe the fundamental theorem of line integrals, because the fundamental theorem of calculus becomes a special case of it. Yeah.
Can you move the camera?
Whoa, is that too far over? Sorry, yeah. If f of x, y is a continuous vector field, maybe it's f1 of x, y, I plus f2 of x, y, j. Have it there. Yeah, is continuous. That is, f1 and f2 are continuous. The book might use little f and little g instead of f1 and f2. It's continuous along a smooth curve C, given parametrically by a vector valued function R of t, t going from A to B. And f is also the gradient of some function phi. What do we say? What do we call a function that was the gradient of another function, of a scalar function? This vector field is the gradient of some scalar field. We called it conservative when we said phi is a potential. So if f is conservative and continuous along a smooth curve, that was the definition of conservative. Then this actually isn't too hard to prove for the common case I'm trying to say. Then the integral f dot dr, this vector line integral that represents, among other things, work along a path, is evaluatable by taking f at the final point if C goes from a point x naught, y naught, its initial point, to another point x1, y1. You just take capital F at x naught, y naught, x1, y1, final point, phi, minus phi at the initial point x naught, y naught. That look familiar, I hope. If this is in one dimension, then the dot product produces just the ordinary product, right? And phi is then the derivative, just a derivative with respect to x. And what we're saying is if phi is, if f is an antiderivative of phi, then you take phi of b minus phi of a. This becomes the fundamental theorem of calculus if it's in one dimension. But now this generalizes this to two dimensions, and you can do this in higher dimensions also. So we'll call this the fundamental theorem. That's what the book calls it. Other books call it something similar, not necessarily the same name. Fundamental theorem of line integrals, which in the fundamental theorem of calculus is a special case. And it says, all you need to do to evaluate a line integral if f is conservative is plug in the endpoint, plug in the initial point, take the difference, just like you did in calculus. How easy, right? So you can think of this like an antiderivative. It's the potential acts like an antiderivative in more dimensions. And that means something very interesting. Suppose I'm in a conservative field like gravity or electric field, right, or conservative fields. And I move from point A to point B, and I want to know how much work is done along the path, and it's really complicated. Is it hard to calculate? I can find a potential. It doesn't matter which path I take, if I go like that, or spiral in here to the, doesn't matter what path I take, the value of the line integral is the same. It's just the potential at the final point minus the potential at the beginning point. And that's it. It doesn't, it's path independent, we say. So I'll reiterate that next time, but that's kind of a exciting and fascinating thing. These things aren't necessarily hard to calculate, no matter how complicated the path, when the vector field happens to be conservative like gravity. All right, so I didn't give you the homework yet. Try all of these. This won't have the fundamental theorem of line integral. We'll do that next time, but oh gosh. Get in here. Good one. Oh, that's because I didn't need it. No, I do. I guess I'll have to give this to you next time. Did I give you 15-2 last time?
You said last time that was for if we wanted to.
Yeah, 15-2 is the line integral. Just do 15-2, the same ones I gave you last time. But finish them all now, because that's the vector line integrals. We didn't get much. Finish 15-2, so powerful after them. I have up here if you want. Okay. Thank you, everybody.